Hablar en inglés.
Sí, sí, sí.
Todos los que he hablado.
Hombre, hay mayoría de españoles, pero
Ya,
tenemos
vale.
otra comunidad. Hay una chica india que estuvo trabajando en China.
¿Ah?
Quieres preguntarle alguna cosa de burocracia o de costumbre.
Sí.
Estuvimos charlando así con Juan, estuve trabajando un poco de los efectos y quería preguntar por el tema de la geometría, si eso serviría, ¿en qué serviría para revelar más efectivamente de ese tipo de objetos virtuales para los que continúan el sistema?
No, ya no muestre más la
Porque no puedo usar el espectro completo de para cortar. Sí, claro. Así que hombre, a mí me gustaría aprender a usar. Ya no lo has hecho.
Ya está la chava.
Lo que pasa es que no te lo has hecho todavía.
No, pero con lo que él tiene lo identifica. Entonces, es estos, ¿no?
Claro, yo ya las tengo más o menos.
Habrá buscado uno, supongo.
Y
voy a ponerlo a grabar.
Pero lo que pasa es que y mira, la clasificación que usé ahora, la recogí como que vi, en realidad se me hace las clases principales del ejemplo, y esto sale como lo que no entiendo.
Ha sido justo antes, menos mal. Nada.
Que se note que estamos en periodo estacional.
Buscar qué probabilidad tiene la semifinalidad. Eso yo probaría primero. Sí, para el plan de tiene también fotometría en sí,
Okay, so let's start. Today, it's a pleasure to introduce Diego Cruces. He recently defended the PhD at the Universidad de Barcelona, and he's going to Beijing in trying to on the way to Beijing for a postdoc soon. He's from Teruel, so it's a local. This is not usual. Today he's going to give us a talk about the non-perturbative description of cosmological inflation. All yours.
So thank you very much, Juan. Thank you very much for the opportunity to talk here. As Juan said, I'm a local, so I'm happy to be able to talk here. And today I'm going to talk about cosmological inflation, which probably is a topic which is a bit off of the Institute here. But I think it is worthy to share our impressions. And I will try to do like a very broad introduction. And my goal today is that you understand why I want to study inflation in a non-perturbative way. The second part of the talk is more about the more detailed mathematics, but I mean, if you understand the first part, I'm completely happy with that. So, if you have some questions, please do not hesitate to interrupt me at any point, because I really want to motivate why I want to study inflation in a non-perturbative way. Okay. So yeah, let me start. So yeah, as I said, the introduction and motivation will be like the most important part of the talk, and after that, if I have time, I will talk about the different techniques, the different non-perturbative techniques to study inflation. By non-perturbative, of course, I mean that I'm not doing a Taylor expansion basically. Okay, so yeah, without further ado, let me start. Okay. So first of all, what is inflation? Why do we need inflation? And well, the reason is very simple. So before inflation, we had a lambda CDM model for the evolution of our universe. And one of the characteristics of this model is that the moving Hubble radius, which is basically the observable universe, is always growing with time. We are in radiation domination is growing with some scale, with some factor, some exponent there. We are in matter dominating with some other. But one of the characteristics of this model is that, for example, if we plot here a conformal diagram, where I am plotting like the past like cone of some observer at some point, one of the features of the model is that, for example, if I plot here a line, let's say this orange line, I have that different patches in the line are not in causal contact, as you can see here. Okay, so these paths never talk with this point here, nor with this point here. So this is in principle not a problem of the model, it's just a feature of the model. So if these two patches do not talk with each other in the previous evolution of the universe, that would mean that they didn't thermalize, so there is no reason a priori. Yes?
Sorry, the x-axis is space.
Yes.
Distance.
Yes. So yeah, so this patch is far away from this one in the sky, let's say. So they didn't have time to talk to each other, so there is no reason to think that the universe should be the same at all in every direction of the sky. But then we went to this observation done by Ciencias and Wilson in 1964, and we found that the whole universe is completely homogeneous. Okay, so we receive a radiation from the cosmic microwave background, which is the recombination epoch, and we receive the same radiation approximately from all directions of the sky, of sky. And precisely this radiation is coming from this orange line. So as I said, why should this orange line be completely, why the radiation coming from this orange line should be completely homogeneous if the patches are not in causal contact? Okay, so this is a problem that we have. This is that we have in the model. This is the so-called horizon problem. There were some other problems with the standard lambda CDM model of the universe, but for me this is the most important one. So yes, in principle I would expect that here I have, for example, a red spot, a blue spot, and different spots here. But I'm seeing the same everywhere. Okay, so this is the so-called horizon problem, and it was one of the problems that motivated the formulation of cosmological inflation. Okay, so cosmological inflation, the solution is very simple. So in the standard lambda CDM model of the universe, we have that the co-moving horizon is always growing, as I said. So if I have a problem when the co-moving horizon is always growing, let's make it decrease. Okay? And this is this. Here maybe there are too many formulas, but this is the idea of the problem. If I have a problem when the co-moving horizon is growing, let's make it decrease. Okay? So if I make the horizon decrease, what is happening is that the singularity of general relativity, which is the beginning of the universe, let's say, is getting pushed away to the infinite past. Okay? So now I don't have the beginning of the universe here in the Big Bang. I have something before, which is inflation. And because I have something before, if I trace the past light cone of the different patches of the universe, I see that they were in causal contact before. Okay? So if they were in causal contact, it means that they thermalized. So I have now a dynamical explanation why the universe is so homogeneous on large scales. Okay? So the way we usually model this decreasing of the moving horizon is with the introduction of a negative pressure fluid. Okay? And a negative pressure fluid is modeled in the simplest way. I'm only talking about the simplest model of inflation with a scalar field. This phi here is a scalar field. Okay? So this scalar field, if I give some conditions to this scalar field, I will have a universe field with a negative pressure fluid. Okay? And with this negative pressure fluid, I achieve the decreasing of the co-moving factor that the co-moving scale that horizon that I'm looking for. Okay? But very importantly, those are just the equation of motion for the field, the Klein-Gordon equation of motion and the energy constraint. It would be the evolution of the Hubble parameter. Very importantly, this is one of the most important things of inflation, is that if I want to have a negative pressure fluid, the field must satisfy this condition here. Okay, so I need a very small velocity of the field, which is related with the variation of the Hubble parameter. So during inflation, the Hubble parameter is almost constant, okay, because of this condition here. And like this, I have inflation, okay. But of course, the CMB is not the picture that I showed before. That was the picture detected by Ciencias and Wilson, and now we have a way more, like, much more precise satellite, which is Planck, basically. And in this satellite, we can detect the radiation of the CMB, and we will see that the CMB contains also small inhomogeneities. So with inflation, I have already solved the problem that the CMB is completely homogeneous. But could I also explain these inhomogeneities with inflation? That would be awesome, right? Because I have like I have two things with one solution, which is inflation. Okay, and we will see in a bit that we can do it. Okay, so with inflation, I'm not trying to explain all the different inhomogeneities here. For example, here you can see can be explaining this inhomogeneity. So this is this x-axis will be like the separation of the inhomogeneities somehow. Okay. So if I am in this part here, I am studying inhomogeneities, the correlation between inhomogeneities that are very close. And here at the beginning, I am studying inhomogeneities which are very far away to each other. And the ones that are very far away to each other are the ones that are very sensible to the initial conditions. Okay. So the initial conditions are the ones that can be provided by cosmological inflation. And I will explain in a bit how this cosmological inflation can provide the initial conditions. Okay. So as I said, I have explained with inflation the homogeneous evolution of the universe. I have explained why the CMB is so homogeneous. So can I also explain the inhomogeneities? And if you look here at the previous slide, you see that I introduce a scalar field. Okay, but this scalar field, of course, is quantum. This scalar field contains vacuum fluctuations because it's a quantum scalar field. So if it contains vacuum fluctuations, this means that I have some fluctuations apart from the homogeneous evolution. Okay, so this quantum fluctuations, okay, will back react on the metric, and what I can do is to expand the metric because I assume that the quantum fluctuations are very small, right? So I can expand the full quantum field into an homogeneous value, which would be the responsible to explaining the green plot that I showed before. Sorry, the green sky, the picture taken by Ciencias and Wilson. And then I have some small inhomogeneities which are given by quantum fluctuations of this field. Okay, and these inhomogeneities will back react on the metric. Okay, so here just to see that I no longer have a Freeman-Robertson-Walker metric. I have some other inhomogeneities which are rather complicated. But the point is that by doing this, what I can do is just to linearize the Einstein equations. Okay. I just expand. I have at first order, I will have the homogeneous equation that I explained at the beginning. And at first order, I just apply the Einstein equations here. And I obtain a very simple equation for a quantity that I'm not going to enter into detail how we obtain this quantity. It's gauge invariant, so it's observable. That's the only important thing. Okay. But I obtain an equation of motion, a very simple equation of motion for the linearized variables. Okay, so for the small inhomogeneities. So now I can study the small inhomogeneities here. Okay, so how do I relate these small inhomogeneities to what we observe in the CMB? Okay, and this is more or less the idea. Okay, so if I study some characteristic scales of the inhomogeneities during inflation, I will have that these characteristic scales will exceed the horizon at some point during inflation, because as I said, the Hubble parameter is almost constant during inflation. This blue line is the Hubble parameter, okay, and this is a characteristic scale for the fluctuations. Okay, so they exceed at some point the Hubble horizon, they get outside the horizon, And then when the Hubble parameter starts growing again in the standard Big Bang evolution of the universe, these scales will enter at some point into the observable universe. Okay, and when they enter here, for example, this orange line refers to the scales that enter the universe when the CMB is generated. Okay, so if I measure here, I can trace back these inhomogeneities and explain them with inflation. Okay, so this is more or less the idea. So very importantly, if I can explain, if I want to explain this in inflation, during inflation, very importantly, these inhomogeneities will be at super-horizon scales. Okay, so everything which is below the blue line is sub-horizon scales, above the blue line is super-horizon scales. So during inflation, these inhomogeneities are at super-horizon scales. Okay, this means that I can neglect any spatial gradient. Okay, because the wavelength of the fluctuations is way larger than the horizon itself. So if I take a special derivative, it will be zero, basically. Okay, so I can neglect this, and I have even a simpler equation for the fluctuations, for the small fluctuations, which has this very simple solution. Okay, and with this, I can compute some. Those are just in definitions. I can compute some observables, such as the power spectrum of the spectral index. Basically, is the k-dependence of the power spectrum. And this is where things become interesting. The point is that I can measure this, I can measure many things in the, I can measure both the power spectrum and the spectral index in the CMB. Okay, so can I explain what I measure with this theory of inflation? And the answer is that yes, but not with any theory of inflation, but with a very specific inflationary regime, which is the slow roll inflation. Okay, so the slow roll inflation, the spectral index measured in the CMB is compatible with this slow roll inflation. Slow roll inflation is very simple to understand. So I have a potential, I have here the field, and the field is rolling down the potential. Okay, just a ball that I throw it in a potential. This is rolling down. But in order to have slow roll inflation, I need that the field has almost constant velocity. Okay, so it's rolling down with almost constant velocity. So I neglect the acceleration. Okay, so this is the regime, this inflationary regime with almost constant velocity that can explain what I observe in the CMB. Okay, the fluctuations around here that I observe in the CMB. Only this regime, this slow roll inflation regime. Okay. Furthermore, apart from that, in the CMB, we also measure, I said that the spectral index in the CMB is compatible with the slow roll, but as I said also in the CMB, we can also measure the power spectrum and the non-Gaussianity. This, if I tell you this, probably you will not understand what I mean by this, but it is better understood here. What does the power spectrum mean and what does small non-Gaussianity mean? Okay. So basically, the power spectrum is related with the variance of the probability distribution of the amplitude of the perturbations. Okay. So if I have a very small power spectrum with small non-Gaussianities, this means that the amplitude of my fluctuations, okay, are distributed following a Gaussian, like here in this plot, where which is very narrow Gaussian, because the power spectrum is basically the variance of the Gaussian. Okay, so you have a Gaussian which is very narrow around zero. So this means that of course all the fluctuations are inside this Gaussian. So all the fluctuations are small, basically. So I don't have large fluctuations anymore. That those numbers are put by hand, but you can imagine that if the variants are here, if I want to have a large fluctuation, I would have to go like 10 to the 5 sigma away from the mean, something like this. So this is telling us that the approximation that I did at the beginning to assume that the inhomogeneities are very small compared to the evolution of the background is a very good approximation in a slow roll. Okay? In a slow roll, well, not in a slow roll, but in the scales measured by the CMB, because what I measure in the CMB is very small. Okay? But now I have this question. Right? So why should I always impose that I have a slow roll inflation? Okay. And the point is that there is no reason a priori, because the CMB is the last thing that we can observe in our universe. Okay? Because beyond that, the universe was opaque, because the CMB is the first light that we observe from our universe. So everything that happens here, we actually don't know what is going on here. Okay. So even if I said that I need a slow roll in which all the fluctuations are small, if I need a slow roll to explain the CMB, because here I don't have any observational constraint, I can have here whatever other regime of inflation that I want. Okay. So if you see it from the potential point of view, I need a slow roll here in order to explain the CMB, which would be this orange line, but here, that would correspond to this green line, I don't have any restriction, I don't have any constraint, because actually the CMB is only accessible to these scales here. So here, I can have whatever I want. So I can say that, okay, I want a slow roll always, but this is quite boring, let's say, because we already know what happens, and there is nothing interesting there, apart from these small inhomogeneities. But but I can imagine that I have some other things, and let's see what happens if I have some other thing, for example, as an inflection point in the potential. Let me imagine that instead of having this, which would be the boring part, where I know how everything is going, let me imagine that I have an inflection point. Okay, so that would correspond to what we call ultra slow roll inflation. So if I have an inflection point, of course, the velocity is no longer constant. I cannot do this approximation. I have to neglect in this point the gradient of the potential. And very interestingly, what happens here is that the power spectrum is exponentially growing. Okay. So what I said before about the power spectrum that is related with the variance of the probability distribution, if I have a regime of inflation in which the power spectrum is exponentially growing, this means that because the power spectrum is related with the variance of the probability distribution, this means that the probability distribution during this ultra slow roll phase is getting broader and broader. It's getting broader exponentially because the power spectrum is exponentially growing. Okay? And the power spectrum is basically the value. So I have something which is exponentially getting broader. So this means that I'm reaching values of the perturbations which are very large. Okay? And probably these values cannot be explained with perturbations here. Okay? So large fluctuations are more probable. And you can say to me now, okay, so you have tell us all this because you want to have a large fluctuation, but why do you want to have large fluctuation, right? I mean, is there something interesting on having large fluctuation? And the answer is that yes, that there is a very interesting thing about having large fluctuation during inflation, which is that when these large fluctuations re-enter the horizon, okay, so let me go back to this plot here. So imagine that I have here a large fluctuation. When this large fluctuation re-enter the horizon here, it can gravitationally collapse and form a black hole. Okay, and this is in the so-called primordial black holes that probably you have heard about it. So these primordial black holes have like very, very interesting phenomenology. Okay, so they can, for example, constitute some non-negligible fraction of dark matter. There are even some models that they are saying that these primordial black holes could represent the whole dark matter. So we can forget about actions or whatever. And also, they can represent, for example, the seeds of the supermassive black holes that we observe in the center of some galaxies. The point here is that, if I understand correctly, I'm not an expert on that, but we observe like very large black holes in the center of some galaxies, which are very far away, a very large redshift, right? So there is no dynamical accretion procedure to get these very, very large black holes so early in the universe, right? If we had like some seed at the beginning, which is already a black hole, they can explain those supermassive black holes, okay? So they are very interesting, they have very interesting phenomenology, these primordial black holes. There is also some people that say that they could represent like even LIGO Virgo events, these primordial black holes. I have heard even some people saying that we have already detected the primordial black holes, but I don't want to be very optimistic. So I just wanted to motivate that these primordial black holes are very interesting, and they come from these large fluctuations in inflation. Okay, well, this is one way of producing them. There is some other ways, but they are even more, I would say, exotic. Okay, but of course, if I want to really understand primordial black holes, and I really want to make some predictions about the abundance of these primordial black holes in the universe or whatever, I really need to understand this large fluctuation during inflation. Okay, but there are some problems here. So the large fluctuations, which are large, large fluctuations are large. So because they are large, probably perturbation theory, what I did, is no longer enough, right? So I assume for perturbation theory that the inhomogeneities are very, very small compared to the background. But here this is no longer the case because they are large. They are also located in the tail of the probability distribution, as I said. So the tail of the probability distribution, anything that you change in the inflationary dynamics would change slightly the tail. And because if I want to compute like the abundance here, I have to integrate from here on. If I have any small change here, the integral here for the primordial black holes will be exponentially affected. Okay, so I need like very, very precise way of studying these large fluctuations. So I don't only need something which is beyond perturbation theory, but I also need something which is very, very precise to study the large fluctuations. And also, as I said, they are generated beyond the typical slow roll, which is the one responsible for the CMB. So I also need something which does not rely on slow roll approximations. So as you can see, this is not an easy task. I really need to go into it, and this is what I did during my PhD, basically. So yeah. So for me, this is like the motivation why I want to study the large fluctuations during inflation. This is the most important part of the talk. From now on, I'm going to explain how I do this. But for me, the main thing that I wanted to do was to motivate why I want to study the large fluctuations. So I think that if you have some questions, now is a good moment. Yeah.
So if those large fluctuations are rare, would there be enough of them to account for the supermassive black holes that we see?
Yes, actually, I mean they are rare, of course, but they can account for, they can even account for the whole dark matter. So because they are very massive, even if they are very large fluctuations, because they are black holes, they are very massive. I mean, black holes of this size have the same mass as the Earth. So even if they are very, very small, they can account. I mean, there are some models in which they explain all the supermassive black holes and also the dark matter with the same procedure. So yeah, even there are even like a lot of problems now because there are a lot of models which are overproducing primordial black holes. So there should be even more dark matter than what we observe. Okay. Yeah.
Are they predicted to be somehow correlated with the baryon distributions, or they can be everywhere?
The baryon.
The primordial black holes.
Yeah.
So they should be the ones that form the black holes in the first galaxies, no?
Yeah.
In the center of the first galaxy. But apart from those that are, let's say, surrounded by baryons,
yeah,
are they the prediction is that they will be anywhere. So there will be many of them. Some of them will end up in the center of galaxies, but there will be also a large distribution of them.
Exactly. And they will like form halos and in the same way as the galaxies.
They will mimic the dark matter in that sense.
Yes. That's why they are so interesting because they are gravitationally collapsed as any other fluctuation. they will like mimic the dark matter and everything. So, yeah.
I don't remember exactly how Hawking radiation goes. Do you not expect them to evaporate in all this time?
That's a good question. Yeah. So it depends on the size of the black hole. So if you go here, okay, depending, because the size of the black hole and the mass depends on when these fluctuations is re-entering the horizon. Okay, so the later is re-entering the horizon, the larger is the black hole. So for example, the black hole that re-entered the horizon very early in the radiation dominated universe, even if these fluctuations create a black hole, this black hole would be evaporated by now because of Hawking evaporation. But for example, the one that re-entered the horizon later on, those black holes would still be in our universe.
Why don't they accrete?
They do.
As in, if they are everywhere,
yeah,
to explain dark matter, you still don't see them, so they accrete?
Well, there are. Maybe I should have put because I'm not an expert.
In the galaxy, there's very little matter.
I mean,
they're in the center of the galaxy, forming the AGN, they do appear.
There are.
But I don't know, I find it kind of counterintuitive that you wouldn't see them at all. Like no observational evidence that the halo of the galaxy is full of black holes.
There's an estimated 100 to 1,000 million black holes in the Milky Way, in interstellar space, and we don't see them because they are floating. They are not in the.
The point is that you have to imagine this black hole, which are very, very small. In order to avoid, there are observational constraints, of course, for some mass range of these primordial black holes, but there are some gap in which there are no observational constraints because you cannot detect them via micro lensing or anything because they are so small. But still, they affect to the dark matter. They mimic the dark matter and everything. So I should have put like this plot of the constraints, and you will see that there is a gap there. Everyone is trying to generate black holes, obviously in that gap. Okay. Any other question? Okay, so okay, I hope I motivated you to go beyond perturbation theory in inflation. So let's explain what are the techniques that we use in order to go to beyond perturbation theory in inflation. And the first technique is the gradient expansion. Okay, so this technique basically is based on the fact, it takes advantage on the fact that we are interested on, as I said before, on the long wavelength limit of perturbations. Okay, so here you can see it very clearly. If I have a long wavelength perturbation, like this one, if I compare it with the size of the universe, at some point, this perturbation will act like a shift in the constant values, in the homogeneous values of the universe. Okay, this is basically what the approximation is telling us. So even if this constant shift on the homogeneous value is not the same constant as let's say as the background, at the full background, okay, because I am doing this approximation, I can still describe this patch here, this small circle here, with the homogeneous equations, as you can see here. And the evolution of this patch here will be different from the one of this patch, from the one of this patch, from the one of this patch. And when I combine the statistics of all the patches together, that I can describe every one of the patches, I can describe with the homogeneous equation. That's the advantage of this approximation. When I compare the statistics, I can get some statistics about the fluctuations in a fully non-perturbative way, because those equations are non-perturbative. I haven't done any Taylor expansion here. The only thing that I'm doing is to assume that they are very large compared to the horizon, but as I said before, I am actually interested in this region because I am outside the horizon. Okay. So this is the idea of gradient expansion. So if you want to compare it with perturbation theory, okay, in order to see it better, the range of validity of perturbation theory is this would be like the amplitude of the fluctuations. So I have like in perturbation theory I can study fluctuations at all scales, no matter if I am inside the horizon or outside, but with very small amplitude. And on the other hand, with gradient expansion, I can only explain, I can only describe the fluctuations which are very well outside the horizon, but I don't care what are the amplitude of those fluctuations because I can already study them. Okay, and as you can see here, there are like overlapping, of course, of the two methods here, and it's very interesting to study this overlapping because naively, and this is what it should happen, you would expect that if I take the long wavelength limit of perturbation theory, so I go here through the blue line, and if I take the small amplitude limit of gradient expansion, so I go down in this orange line, I should recover exactly the same result, right? I mean, this is a consistency check, and then you do it, and what happens is that with perturbation theory, you recover this solution, and with gradient expansion, when you go to the small limit, you recover only of the two solutions, you recover only the constant one. So there is something weird happening here, right? And this is something that we realized during my PhD, okay? And this is like everything in my PhD has been based on this observation, okay? Which is a very simple observation, but that no one did before for a very simple reason. And the reason is that probably there were a lot of people that knew this, that with the linear perturbation theory, you recover two modes, and with the linearization of gradient expansion, you only recover one. But the point is that this mode is always, well, it's usually decaying with time. Why? Because epsilon1 in a slow roll is constant. So because epsilon1 in a slow roll is constant, and the scale factor during inflation is exponentially growing, this is exponentially decaying, so I don't care. But what happens if I want to produce primordial black holes? That I have that epsilon1 is exponentially decreasing. Okay? Instead of having it constant, I have that is exponentially decreasing. So what happens here is that if epsilon1 is exponentially decreasing, this is like going as a to the 6. This means that this factor here is exponentially growing in regimes beyond the slow roll. Okay? So this difference now is crucial if I want to study primordial black holes. Okay? And this difference comes from some factors that I neglected here. This is not important, but anyway. It comes from some factor that contains a Laplacian, but well, that should go to 0 at super-horizon scales. But the point is that are non-local terms. So they have like 1 over Laplacian square, let's say, mathematically speaking. So they do not cancel in the k going to 0 limit. Okay, even if they have this, they do not cancel there. So you have really to take account of those if you want to describe also this mode. Okay, this is very important. This is what we did in this paper. And okay, so this was one of the problems of gradient expansion. Okay, and another problem that we can imagine is that in gradient expansion, the initial conditions for gradient expansion are not really well defined. The reason is that gradient expansion, as I said, is only valid at super-horizon scales. Okay, but the initial conditions for inflation, we usually give them at sub-horizon scales. The reason is very technical, but basically we cannot define a vacuum in some space that is not Minkowski. And a sub-horizon scale, you can do the approximation that the space is Minkowski, so you can do that. But you cannot do that in gradient expansion because you are a super-horizon scale. Okay, so you have to combine gradient expansion, which is the non-perturbative technique that I have just explained, with some other techniques that give us the initial condition. Okay, and this is the so-called stochastic approximation. Okay, so I have to combine the two techniques. Okay, so I want to describe the evolution of the full quantum field in a fully non-perturbative way, okay? Because I want to describe, as I said, the tail of the probability distribution. And what I do is to split the full quantum field into two parts. On one hand, I have the infrared part, okay, which is for scales, for very large scales compared to the horizon. And here I use gradient expansion, which is the technique that I said. And this will give me the equation of motion, okay. But on the other hand, in order to complement the gradient expansion with some initial conditions, I for the ultraviolet part, which are the modes which are inside the horizon, I use linear perturbation theory because inside the horizon the mode didn't have time to grow enough, so I can still trust perturbation theory, and this will give me some noises to the equation of motion. Okay, this is why this is called the stochastic approach to inflation, because I have a stochastic differential equation, which is a differential equation with a term which is a noise, a term which is completely random. Okay, and let me explain, not with maths, but with some picture that I try to do, why this part, the ultraviolet part, is giving me like some noises, some completely random time. Okay, and this is more or less the idea. Okay, so I have a patch here that is evolving following the equations of motion of gradient expansion. Okay, this patch, the mean value is following a gradient expansion. But then inside the patch, I have some fluctuations here. Okay, so what happened during inflation? That these fluctuations get stretched out. Like I am throwing here, and some other person is throwing there, so they get stretched. And at some point, they start contributing the evolution of the Hubble patch here, because they are contributing here with a constant value. Okay, so they are entering into the gradient expansion regime. Okay, and then I have another mode, another fluctuation as to horizon space that get stretched again. Okay, so then I have here another contribution to the evolution of the gradient of the patch itself. So it's like a patch and at every time step, this patch is like moving because it's receiving different contributions from the different modes that I'm stretching every time. Okay, so this is the idea more or less behind the noises. Okay, and very importantly, you can imagine that if I want to do perturbation theory, because as I said, for the noises, I'm just doing perturbation theory. If I want to do perturbation theory for this blue line here, I have to use a background which is not the dot background here, but a background which is the dot background, but also affected by the noise that comes from the solid black line. Okay, so I have to compute. This is a very technical problem, but it's very important. I have to compute linear perturbation theory over a background which is stochastic. This is quite complicated. But anyway, I will go back here. Okay, so what is usually done typically in the literature until some years ago? Okay, so they generate the stochastic formalism, they formulate the stochastic formalism. Okay, but here in the infrared part, they used to use the naive leading ordering gradient expansion, which is neglecting all those terms. But I already justified that those terms can actually play a role for the description, and they play a very important role for the description of the long wavelength inhomogeneities if I am in some regime which is not a slow roll, which are the regime that I'm interested in. Okay, and this is only valid at leading ordering epsilon 1. Okay, but of course the tail of the distribution is very sensible to all epsilon 1 effects, so this is probably not valid anyway. Okay, so now don't get scared about this this slide here, but yes, I just wanted to show this slide in order for you to see what I just said. So I have the equation of motion for the infrared modes here, okay, which is exactly the same equation of motion as in the background, in an homogeneous background. So this is the equation of motion of an homogeneous background, and then I have some noises, okay. But as I said, those noises must be computed by solving linear perturbation theory over a background which is stochastic. Okay, so here you can see a problem. I need to solve this equation, and in order to solve this equation, I need to know the noises. But in order to know the noises, I need to solve the equation before. I have like some recursive problem here, because of course, I mean, these parameters here will depend on the solution of the infrared part. Okay, so in order to compute the noises, I need to solve the equation, and in order to solve the equation, I need to compute the noises. So this is what is actually really difficult in stochastic inflation. Okay. So yeah, so then I can sum up and say that we have two main problems with the usual stochastic inflation, stochastic approach to inflation. The first problem is that basically I am neglecting these Nabla square terms. Okay, and this is not enough. I mean, this might be enough maybe to study the mean value or the variance of the probability distribution, but if I want to study the tail of the probability distribution where the fluctuation responsible for primordial black holes are, this is not enough, okay? I need to include these Nabla square terms, which is very important. So this is the first problem here. And then the second problem is how do we compute these noises in this background, which is stochastically correct, okay? Because as I said, this is a technical problem, but a very difficult to solve problem. So I guess that based on what I said about gradient expansion, that we were able to formulate gradient expansion including these Nabla square terms, you could guess that this problem we solved in my thesis. So we formulated a stochastic approach to inflation in which we included the Nabla square terms. Okay, and it was not done before in the literature. Okay, and we were able to do it in this couple of papers. And then we have finally a stochastic approach which is valid at all orders in epsilon, so it is very, very precise to study the tail of the probability distribution. This stochastic approach is a monster, as you can see, but in principle you have it, you can solve it. But now, I want to solve it, okay, so let's go to the second problem. I want to solve the previous system that I already have it, finally, and but in order to solve it, I have to compute the noises in this stochastically corrected background. Okay, so let me remind you the problem of solving this. So we must solve this equation here in order to characterize the noises, but we need the noises in order to know the time dependence of this function here. So in order to solve this equation. So I need to solve the equation to know the noises, but I need the noises to solve the equation. So this is something that is very difficult to handle with, because also I am talking about the stochastic equations in which I don't have to solve the equation once because this is meaningless. I have to solve the equation many times because I am interested on the statistics of the equations. So if this is not, if I cannot solve this in a very effective way, then it is impossible because I have to solve this like 10 to the 5 times. So if it is not effective, it will take years for me to solve it. Okay. So it can be done numerically, but it's computationally very expensive. I only know one group in Finland that they did it, and they had to borrow like this supercomputer that they had there for 2 months, and the statistics were not very good even. So yeah, it's very, very expensive. So it is maybe more clever to do some approximations, okay? So the approximation that we usually do, or that they are done in the literature, one of them is to assume that we have a fixed de Sitter background. So the idea of having a fixed de Sitter background is that I have fluctuations of the field, but these fluctuations do not backreact on the metric. So I only have fluctuations of the field, and the metric is completely homogeneous. But of course, this is forgetting about all the order epsilon effects. For example, I cannot reproduce with this approximation, not even the spectral index that we observe in the CMB. So this is not really a very good approximation. It can be done, but it's not really a very good approximation. And the second approximation that people usually do is, instead of solving this equation, in which those variables here are completely stochastic, so instead of solving the linear equation for a stochastic background, I do it for a deterministic background, a background which is the same for all the patches. Okay, so if you want, instead of solving the linear perturbation theory over this background, which is affected also for this line, I solve the linear perturbation theory for the dot line every time. Okay, but we check, and I mean it can be justified maybe qualitatively, that by doing this approximation, we are actually recovering linear perturbation theory. So we are losing all the power that we wanted to, yeah. I mean, we are losing all the power of the stochastic formalism. So this is not really a good idea. Okay. So although we were able to solve the same in the first problem, we have now a stochastic formalism which is able to describe, in principle, to describe the Taylor probability distribution with a lot of accuracy. We have the formalism, but we don't know how to solve it. Okay. So, and in order to check these two things, that these two things are actually what I have just said, we did like some simulations, for example. And this, for example, we simulated a stochastic formalism for inflationary regime that has an inflection point. Okay, so what I said before, I have an inflection point. So because I have an inflection point, at some point the power spectrum is exponentially growing with time. Okay, so we solve the stochastic equations and we compare with linear perturbation theory in this case, in which I'm doing this approximation. So I know that I have to recover linear perturbation theory. It's just a consistency check. But what happens? That I only recover linear perturbation theory if I use our formalism, in which I am taking into account these Nabla square terms. If I use the other formalism, I'm recovering something which is completely different. So this is a consistency check that our formalism is working, at least in this regime in which I have to recover linear perturbation theory. Okay? So, yeah, let me conclude already. So, as I said at the beginning, I motivate. If I have during inflation a growth in the power spectrum, this only happens beyond the slow run, I can generate large inhomogeneities which can produce primordial black holes in a more probable way. But of course, these large inhomogeneities might be described beyond perturbation theory. So, for example, I can use I wrote here 2 times, for example. I can do the stochastic formalism. Okay. However, the stochastic formalism, although we know that now we have a stochastic formalism that is able to capture these non-perturbative effects in a very precise way, it is really difficult to solve practically those equations, okay? Because it would take years, and we have to find some other approximations in order to solve them, and this is basically what we are doing right now. So how can we quantify the error when using the deterministic noises? Okay, so this is basically, is there some approximation that we can do and we can still trust the non-perturbative effects? Okay. And even if I use the deterministic approximation, can this give us some information about the breaking down, for example, of perturbation theory? Because if I know that the two formalisms must coincide, if some of them goes away, this means that probably there is something wrong with the theory, and this could be the breaking down of perturbation theory, which is very important. It's very important to point out when this happens in any theory. Okay. So yeah, that was it. Thank you very much.
Very much, Diego. Very nice talk. Questions?
Yeah.
Okay, so in the first part of the talk, you were talking about how the variation of the scale of the horizon only matters when it crossed.
Yeah.
So when it produced the anomalies, we see the perturbation we see in the cosmic microwave background.
Yeah.
But would the evolution before that time affect the primordial nucleosynthesis?
Yes.
Are there limits on that?
I think they are on the because the primordial nucleosynthesis would be like around this epoch, probably the beginning of the radiation domination. So I think that the limits that are here about the amplitude of the fluctuations, they are not as strong as. Well, I'm talking on memory. I don't really know, but I mean, I think they are constraints here on the amplitude of the fluctuations. I know, but I think that these constraints are not important because, as I said before to him, the primordial black hole that would enter here would be evaporated by now. So I mean, yes, I agree that they could affect the primordial nucleosynthesis, but I think that this is under control. And in fact, we are not interested in this region. We are interested in region about here. So yeah, probably this has been studied. There are some constraints there, and yeah, if you generate primordial black holes there, probably you screw up something. I don't really know what, but
Because even both the evaporation of the black holes that are small enough, or the accretion of the plasma of the bigger ones, would alter the properties of the plasma.
yeah.
Because changes that might be observable too.
Yes. Yeah, I know that there are studies about that. I don't study this part, but I know. I mean, I don't have internet here, but maybe we could show like these constraints of primordial black hole that depends on all these this thing that you are saying. But they are a table with constraints that microlensing, primordial nucleosynthesis, evaporation, all these constraints are taken into account, and still there is like a small gap that you can generate primordial black.
My question is maybe a bit outside of the topic, but I don't really know. So I was wondering, how do you know if the primordial, what's the name, the fluctuations, will form a black hole or a dark matter halo, for example? I mean, is there any?
Okay, so I mean, first of all, it depends when it re-enters the horizon, right? So if I have a fluctuation re-enter the horizon during radiation, it cannot form a halo because it would get thrown away, let's say.
Okay, yeah.
If it is very, very large, then it is you have the gravitational collapse against the pressure of radiation. So if the gravitational collapse wins, then you form a primordial black hole. If not, this fluctuation just vanishes. Okay. Then if you are in matter domination, so your question was that how do I know if I form a primordial black hole or a halo, right? So I think it's the same. I think that if it is large enough, the collapse will be so hard that it will form a primordial black hole. If it is not, they will just get together, two fluctuations, and they will form a halo.
I have a question. What would you need to solve to calculate? So which computational resources would you need? It's something that it's too ambitious and then it's very difficult to. So you need a very large collaboration to get that computing time, or it's something more reasonable?
I think that it's a very large collaboration, and basically it's because of this. Okay, so in order to know the statistics of primordial black holes, okay, we're interested on this part of the probability distribution. So every time I solve the stochastic equations, I get a result which is thrown, let's say, randomly in this probability distribution. What happens that, okay, it's not very expensive to solve once the stochastic equation, it's not very expensive to solve 1,000 times, but if I want to really know the statistics here, I really need to have like a histogram with many realizations, and this is the computationally expensive part that I have to do a lot of statistics. I mean, it's not very difficult to solve once the stochastic equations, but this probably with a very high probability, this solution of the probability of the stochastic equation will be like here or here, but not here. That is where I am interested.
Elios?
Do you have an opinion on the other primordial things like primordial naked singularities or something that there was even like a paper recently? No? They were going for that, like naked singularity instead of black hole, whatever that means. But I don't know, just, if you have an opinion, if you are aware of the concept. I don't know if it is a competing concept or a complementary concept.
I don't really know this thing of primordial naked singularity. I don't know. I mean, probably if they exist, they are not formed with the collapse of fluctuations, of these large fluctuations. Because the collapse of large fluctuations, if they form a primordial black hole, the singularity is inside, so it's not naked. So you don't have any problem. Maybe you can form naked singularities if you collapse some cosmic strings that comes from some phase transitions in the early universe, but I'm not an expert on that. I only talk about primordial fluctuations, and this, in principle, I don't think it can form a naked singular.
Antonio?
Back to this plot. So, since you are only interested in the far right part of the distribution, is there a way to resolve somehow or to approximate the solution so that you can discard all the solutions that you don't really care about?
That's a really good question. There are some works on that. There are like some, I don't remember how it is called, but there is like what we are saying is like, because I am interested in there, so let me make it like the equation that I want to solve, like pre-bias to go to this region. But we have like, there is a similar problem, and it is that in order to go to this tape to resolve the solutions there, I need to know, let's say, like, what is the approximate value of the noises, okay? In order to solve to know the approximate value of the noises, I still have to solve this equation over a stochastic background. So it is not that easy. We are working on that. There are some other groups in France, in Paris, concretely, that they are working on that. And I think, for me, that would be probably the best way to solve this. To give like some pre-bias to the equation, such that instead of solving this, I am solving this, but restricted to the range that I'm interested in. There are some works, but for the moment, there are not very good results.
Could you use machine learning to predict the solution instead of solving the equation?
I don't know. maybe, but I haven't used machine learning in my life. If some of you are expert on that, I'm happy to talk with you for sure.
And related to this, could you think of any set of observations that can probably constrain the shape and the distribution of the noises? Or instead of like doing everything
of the noises, I don't think so. On the probability distribution itself, I think that there are a very good opportunity with the LISA, with the interferometer, because the point is that these primordial black holes, apart from, this is a little bit off topic, but I think it's worth it to say. So when these primordial black holes re-enter the horizon and they collapse, they form they also generate gravitational waves. The gravitational waves, in principle, can be detected by LISA. So if you do this transition between primordial black holes gravitational waves, with LISA, probably you can restrict something here. We are also working on that. There are a lot of papers on this. The main difficulty of this is that I have plotted here a Gaussian probability distribution, but they are high probability that this is not Gaussian. This is not a Gaussian tail. And then predicting the gravitational wave signal with a non-Gaussian tail is very difficult. But there are a lot of work on that. People from Japan, mainly from Japan. But in principle, we will know in 2035, I think, that LISA is flying. Let's see.
Questions? Online attendance, maybe?
Nope.
No? We thank you again. You're dismissed.